A fly lands on a leaf looking for a quick meal. It takes a step, brushes against a tiny hair, and nothing happens. Then it takes one more step, touches a second hair, and in less time than it takes you to blink, the leaf folds shut like a bear trap. The fly is gone. But that leaf has no brain, no nerves, and zero muscle tissue. This rapid movement baffled early scientists for over a century. Charles Darwin ran experiment after experiment, feeding the plants tiny scraps of meat, but even he couldn't fully explain how a leaf could move so suddenly. The fly trap operates by running a literal biological algorithm powered by electricity. It acts as a brainless computer, executing a rigid chain of logical if-then checkpoints before it ever commits to a strike. Inside the trap, a few stiff spikes act as sensors. When an insect bends one, the plant fires off an action potential, the same kind of electrical signal your own nerve cells use to send messages through your body. A single touch does nothing. Out in a bog, a raindrop or a falling twig might hit the leaf. Snapping at every brush would waste an enormous amount of energy. The plant requires proof. That first touch leaves a flush of charged particles, starting a 20-second countdown. This short-term memory holds the signal to compare it against the next. If a second touch lands before the memory fades, the plant confirms live prey and strikes. Lacking muscles, the plant relies on physics. An open trap is bowed outward, storing elastic tension like a bent plastic ruler held under strain. The second signal triggers a sudden shift in cellular water pressure, flipping the curve of the leaf and releasing all that stored energy at once. Scientists call this snap buckling. The trap speed comes from this sudden release of physical tension, dictated by a highly precise memory check. Closing the trap is only the first gate. The lobes initially interlace loosely, leaving gaps while the plant waits for more evidence as the prey thrashes inside. At count 3, the plant produces an internal alarm hormone called jasmonate. This chemical signal prepares the system to begin digestion. Once the plant registers 5 signals, a flood of calcium particles enters the cells, finally triggering the digestive enzymes. The plant uses the total number of touches as data. More struggles indicate a larger insect, and the plant adjusts the volume of enzymes to match the size of the meal. These are mandatory checkpoints. If researchers artificially block that calcium signal, the trap remains bone dry, never producing digestive juice no matter how much the prey struggles. By literally counting the footsteps of its prey, the flytrap prevents itself from spending metabolic energy on false alarms. Venus flytraps live in wet, sandy bogs in the Carolinas, where the soil is almost completely devoid of nitrogen. To survive this environment, the plant evolved to mine nitrogen from living animals instead of the dirt. This specialized survival strategy comes with a strict budget. An individual trap can only open and close between 3 and 12 times in its entire life before it dies off. Snapping and digesting burn a fortune in energy, and the leaf faces a real risk of physically breaking if it has to reopen after a false alarm. This complex counting algorithm is a system of evolutionary accounting designed to prevent the plant from starving to death on its own efforts. In the final stage of a hunt, the trap seals airtight, transforming into a green stomach that dissolves the prey over several days. This process challenges the assumption that memory, counting, and decision-making are exclusive traits of animals with nervous systems. Intelligence is a pattern, a specific way of processing information and executing decisions based on that data. The fly trap replicates this pattern using only water pressure, leaf geometry, and electrical signals. This brainless calculation runs on windowsills everywhere, keeping a hungry plant alive on a strict budget of footsteps and electricity. If you want to see more of the hidden engineering of the living world, subscribe to the channel and give this video a like. Leave a comment with a plant or animal you've always wondered about, and I'll see you in the next one.